Hi, this is Mr. Phillips, and I'd like to talk to you about Activity 8.2 Modified. If you remember, we did not use the cup setup as demonstrated in your book. Instead, what we did was we used a paper spiral held on a wooden skewer above a Bunsen burner. So, you were supposed to make some observations, so here are some possible observations you may have made. And I just said the spiral was stationary at first. It started to spin after we lit the Bunsen burner and held it over the Bunsen burner in the proper position. You may have noticed positioning the spiral over the burner made a big difference as to how quickly it started to spin and also how fast it would spin. Did the spiral have kinetic energy before the Bunsen burner was lit? Well, for practical purposes, it did not have very much kinetic energy before the Bunsen burner was lit. Obviously, it was probably wiggling around a little bit, but it wasn't spinning. Did the spiral have kinetic energy after the Bunsen burner was lit? Well, that depends upon where the spiral was being held. So the spiral began to rotate after it was held in the proper position over the lit Bunsen burner, thus giving the spiral kinetic energy. Remember, kinetic energy is energy in motion. When did the spiral have more kinetic energy? Well, when it was held in the proper position over top of the Bunsen burner. Then it would move at its highest speed if you held it just in the right spot. Did a chemical reaction occur while the Bunsen burner was burning? And how do we know? Well, if the Bunsen burner is burning, then there was definitely a chemical reaction, because burning or combustion is always a chemical reaction. Substances combine with oxygen to make new substances when burning. In this case, the natural gas combined with oxygen to transform into thermal, kinetic, sound, and light energy. So where did the kinetic energy of the rotating spiral come from? How do we know? Well, the kinetic energy of the rotating spiral came from the Bunsen burner burning natural gas. While burning, the chemical energy in the natural gas transformed or converted into thermal energy, heating the air molecules and giving them kinetic energy. And remember from previous experiments, hot air rises. And as the hot air is rising, it's pushing against the spiral at different points, and therefore it causes the spiral to rotate. What made the paper spiral rotate? The kinetic energy of the rotating spiral originates in the chemical energy of the natural gas plus the oxygen when the Bunsen burner was burning the natural gas producing water vapor and carbon dioxide. Now if you notice I have an asterisk beside carbon dioxide. Carbon dioxide is a clear, colorless, odorless gas, and it's one that can also cause problems for you. So you have to be careful with that. Now carbon dioxide is what we also exhale. But if you have too much carbon dioxide around, it can actually give you a headache. It's not the same as carbon monoxide. Carbon monoxide can kill you very quickly. The combustion of the gas with oxygen is a chemical reaction during which new substances are formed from other substances, and chemical energy is transformed into other types of energy, such as thermal energy, and kinetic energy making the air rise and hit the spiral, causing the spiral to spin. So what energy transformations took place in transforming chemical energy into kinetic energy? Well, let's take a look. Some of the chemical energy, or CE, of the Bunsen burner and oxygen is transformed into thermal energy and kinetic energy for the air molecules, which is then transformed into kinetic energy in the spiral. So I drew a little model here for you. So our CE is the natural gas burning, and that causes the air molecules to have or gain more thermal energy and kinetic energy, which in turn causes the spiral to spin because it has kinetic energy and an increase in thermal energy. If you prefer a model like this is a little bit better for us. Now, we have a little bonus part of our notes here. Exothermic versus endothermic reactions. And I just want to put this on here because it's good information to know when we're dealing with chemical and thermal energy. So an exothermic reaction releases thermal energy into the surroundings. The way I think about this is exo means it's exiting the object. So an example would be a fire burning is an exothermic reaction. If I go outside and it's wintertime and I start to feel cold, it's because the thermal energy is leaving my body, is exiting, so that would be an exothermic reaction. An endothermic reaction, on the other hand, absorbs thermal energy from the surroundings. The energy is entering the object. So an ice cube melting in your cup on a hot summer day is an example of an endothermic reaction because it's absorbing thermal energy from the surroundings, causing the ice to melt. So this is similar to the principle behind a refrigerator working. So you have your food that you pick up at the store, maybe you grew it in your garden, which would be amazing, and you put it in the refrigerator. So your food is warmer than the other contents in the refrigerator. And what happens is your food gives off heat to the refrigerator, and in the refrigerator, the basic concept is that there are a whole bunch of little tubes going around that have a gas in it that will it's a liquid that expands into a gas very easily at a low boiling point. And so what will happen then is that that gas will absorb that thermal energy from the food that you put in. And then the refrigerator does its process, and I'll have a video posted for you. And as it goes through the process, it takes the thermal energy out of the food, and it absorbs it in a liquid. It becomes a gas, and then that gas then goes through the system and gets compressed back into a liquid, and then it kicks that thermal energy out into the room that the refrigerator is sitting in. So the key thing to remember is a refrigerator or a freezer does not put cold into the food. It takes the thermal energy out of the food. And another side note would be candles. Well, how do candles work? Because we're talking about chemical energy, and this is combustion. So I thought I'd throw this on here for you real quick as a little trivial thing. So when you light a candle, the heat of the flame melts the wax near the wick. You're not trying to burn the wick, you're trying to burn the candle wax. Because if you just burn the wick, then pretty soon your candle won't be any good because the wick is a small amount of the material of the candle. So the liquid wax is then drawn up the wick by an action called capillary action. And the heat of the flame vaporizes the liquid wax, turning it into a hot gas, and it starts to break down the hydrocarbons into molecules of hydrogen and carbon. And that is why you have a nice flame. And that's all I have for you for Activity 8.2 Modified. Thank you.